Today we're going to look at angle. What is an angle? I thought I knew, but it turns out that, well, I probably know, but I don't think the mathematicians know. And we'll see some differences here. So let's start with our version. This is it. Okay, I talked about the universal movie. Universal movie is a tool that we use so that every frame in that film, in the universal movie, simply shows all objects in the universe, every single atom at a given distance from each other. It's just separation, qualitative separation, and everything is standing still in each frame. So in order to see the universe move, just tiny amounts, from one location to the next, but very tiny amounts in the location, you need to look at 2 frames or more. And 2 frames or more is what we call motion. And the concepts that you see at the bottom there, motion, position, plasma, ether, etc., all those are dynamic concepts. You need at least 2 frames in a universal movie to conceptualize anything that involves motion. On the other hand, static concepts, as the ones you see at the top, the ones in yellow there and blue, those you can see in a single frame, or you can conceptualize in a single frame. And there you see some object, distance, location, existence. Those are all static concepts. You do not have to see anything moving in order to conceptualize those words. And one of them is line. As you can see there, you see a line, which is an object, okay? And what you're staring at is an elongated rectangle. That's what's objectively in front of you. Okay, so what you're looking at, something standing still. It's an object. It's an object because it has shape. That's the reason it's an object. It looks like a 2-dimensional, could be 3, but at least it's got 2 dimensions, right? It's got width and height. Okay, there's no length. Length would be the 3rd dimension on that. Okay, at least we don't see it there. And what you see is an elongated rectangle. It's got 4 edges, okay, et cetera, et cetera. So that's what a line is, objectively. That's what's in front of you. It's not 1D, it's 2D, okay? And it's an elongated rectangle, which is what 2D is. What you have there is a plane. That's objectively what is in front of you. Okay, that's the starting point. Okay, I hope you understood what I just said. One fellow says, he goes through the motions of trying to debunk those ideas. And here's the first notion he puts out. He says, a line is a straight path on a plane that extends forever in both directions with no endpoints. A line segment is part of a line. So a line is one thing, a line segment is something else. It's a part of a line, a segment of a line, right? That has 2 endpoints and is finite in length. Okay, I hope that makes sense to some of you, okay? A ray is a line segment that extends indefinitely in one direction. These are conceptual one-dimensional geometries, meaning that they can only reside in the mind or minds of humans as abstract ideas. Okay? These geometries then can only be represented with illustrations. Okay, so this is his argument, saying that's what a line is. The line is not what I showed you just now, which is an elongated 2-dimensional rectangle. Okay, he's saying something else. And so let's go piece by piece to see what this fellow said. Okay, so see if we can detect all the errors he made, every single one that he made with his description or identification of what a line is. Okay, here it is. Let's go with the first one. He says, a line is a straight path. Well, a path is not a figure. A path, like there you have a plane path, right? Path made by a plane. This one's crooked, it's not straight, okay? But if a path is not a figure, it doesn't even belong in geometry, okay? So a path is a noun in ordinary speech, and it's approximately or something similar to a hole. In order to have a path, you need some ground, for example, right? You need to have something on which you make the path. Just like when you make a hole, you need to have the ground to make the hole into. Not like in mathematical physics, where they have these black holes and they drill them into space. And they're zero-dimensional holes. So you figure that one out. And so this path, which is a verb actually, right, is an itinerary, a trajectory or orbit. In case of orbit, it would be circular, not straight, right? But then you cannot talk about straight. You cannot use the adjective straight to qualify a path, because a path is not a thing, it's a verb, okay? So you used it there. Can it extend forever? Well, then it's not a figure. Again, no figure extends forever, because a figure is that which has shape. Okay, so not only doesn't it belong in geometry, but if it extends forever, it's not a figure, period. And verbs don't extend. So if path is a verb, then you cannot talk about extending it like you would extend a clothesline. Okay? Extends forever, again, he's talking about an itinerary. He's talking about motion. There is no object that extends forever. Whenever you talk about forever, meaning time, eternal, right, or use any of those qualifiers, you're talking about not extending. You're talking about something different. You're saying that the itinerary is never ending. It's it just goes on and on. You could say forever, right? You're talking about motion. You're talking about perpetual motion, and not about a physical object. And no endpoints, again, not a figure. So all those he failed, and that's just in his first sentence. Okay, so there he had trouble qualifying what a line is, okay, because he fails all those points. Not a geometry, not a figure, it's a verb, and there's no verb that extends, and there's no object that extends forever. So he failed all those. But he continues here, he goes on the second line, says a line segment is part of a line. Well, we just held that a line is not a figure, so what is it? Part of an itinerary, I guess. That's what he's saying. Okay, that has two endpoints and is finite in length. Well, we got a problem with that because if it's got two endpoints, you could say it's a line. But if it's just a segment of a line, and a line is an itinerary, all you're talking about is two locations. Those endpoints are locations, and what you have in between are more locations. You're talking about an itinerary. So this line segment is actually a verb that he's conceptualizing there. And it's finite in length, he says, and again, verbs are not finite. Okay, motion is not finite. All motion is infinite if you use that term, not correct, adjective. You can say all verbs are incessant. Every motion is incessant, okay? And verbs don't have endpoints. So again, all those issues he failed in describing what a line is. Okay, so he's got the wrong notions of what is objectively in front of you. Okay, and here's another one that says a ray is a line segment that extends indefinitely in one direction. Well, we have a problem because he already defined line segment as one that has two endpoints. So now he's saying, well, it's a line segment that is missing one endpoint. What was a line segment? An itinerary, because it's a line, and a line is an itinerary. So the line is not a figure, which means a line segment is not a figure, which means an array is not a figure. We're talking about verbs here. Okay, line segment is equal to two endpoints. In other words, that line segment can't be extended indefinitely. Okay, so again, he's got all these errors in conceptualizing what a line is. It's easy to tear all his arguments down. Okay. And then he moves on to the next issue, which is the conceptual issue. He says, these are conceptual, one-dimensional geometries, meaning that they can only reside in the mind or minds of humans as abstract ideas. But we have a problem because a concept is not an object. Okay, so if he's going to talk about figures, there's no such thing as a 1D figure. And if it's a 1D figure, it doesn't belong in geometry. Okay, you can't illustrate the 1D. So he's talking about, geometries can only be represented with illustration. Yeah, geometries can, but not the 1D line. You cannot illustrate a 1D line. Whatever you put on the paper is at least 2D, two-dimensional. An idea is a concept. It's a synonym of the word concept. So they're synonyms. And so idea is not a figure. And again, that means that it doesn't belong in geometry. So he made all these errors in just a couple sentences there. Very interesting, because he just about failed every single one. All I can ask him is that he do a little bit of research and get the basics of geometry, because apparently he lacks an understanding of geometry, basics of physics also, right? Here's the correct definition, okay, which I'll put up again. What are you staring at? I mean, objectively. Well, you see an elongated rectangle. And that rectangle is straight. You can talk about straight, you can qualify it as straight because you use the adjectives to qualify nouns. A line is a noun because it has shape, and for the purposes of physics, purposes of science. Okay, that object there is an elongated rectangle. It's got 4 sides, 2-dimensional. Those sides have edges, so it's got 4 edges. It's got width and height, okay? And you can say it's straight because objects can be said to be straight. You can qualify them with that adjective. What else? If it's straight, it's continuous. Continuous means it's made out of a single piece, not made of parts. Okay, and in contrast, and it's finite. In contrast, the line of mathematics, which is what this fellow apparently was trying to describe or define, right, is an infinite line, meaning it's not an object, it's not a thing. It's 1D, which again, it's not a thing. You can't illustrate a 1D. What they're talking about is an itinerary. They're talking about made of points, meaning locations. What is made of locations? Motion. 2 or more locations makes motion. Okay, so you can see that, and especially if you got the infinite signs there, the negative to positive infinity, they're not talking about a physical object. They're not talking about a geometry, a figure. So that's a line. A line is what you see there. Objectively, that's what's in front of you. Now, if in your mind they force you to say, well, yeah, that's what's there in front of you, but think of it as a 1D line. Well, now you're being subjective. Now you're not talking about what's objectively in front of you, what's coming out of the screen to your eyes. Now you're interpreting that and saying, okay, I'm going to imagine that's a 1D line. But you cannot even imagine a 1D line because there is no such figure in geometry. Okay? That's why they never try to, that's why they can't define the point, the 0D point and the 1D line, because they're not points and they're not lines. They're talking about locations and they're talking about motion. And they call that geometry. So our forefathers, the Greeks, they screwed up from the start. And I'm sure there were people before them where they got a lot of this understanding of geometry, measurement of the land. Okay, so now you know what a line is. Why do we need the line? Well, because we're going to talk about angles. We're going to say, well, how does the line relate to an angle? Does an angle require lines? So that's going to be the issue, right? Remember, what is a line? Just an elongated rectangle in physics, in science. That's what's objectively in front of us, and we look at it objectively. No subjectivity whatsoever, no interpretation. In math, they do something else. They look at that and say, well, you're not staring at a 2D line. You're actually staring at a 1D line, meaning made of points, meaning that it's locations that form motion. That's what they're talking about. Okay, and that's an interpretation. That's subjective. Okay, and that's where the problem comes, because what you're staring at is not what they're describing. There's they don't match. Okay? There's a disconnection there. Okay, so here we bring the universal movie again. Okay, and so for us it's very simple. What is an angle? Well, you have 2 lines, okay, and you have a separation between them. See how easy it was? That's what an angle is. They're connected at one point and not at the other. Okay, so that's an angle. Problems come when they have 0-dimensional angles. Okay, and that's one of the problems, because you have the 0-dimensional angle and they say that's an angle. It's a 0-dimensional angle. Well, not if you define it as connected at one end and not at the other, then they can't be 0-dimensional. Okay? So just keep that in mind, but it's a static concept because we're looking at the end result, not at how we got there. And that's where you're going to see the difference. Okay? Not how we got there, but the end result. A static concept, what's coming out of the screen to your eyes, that doesn't move. It's in a single frame of the universal movie. What do you see? You see 2 lines that are separated. Lines are physical objects. You can describe them as being straight, okay, because you can use the adjective such as straight to qualify a line, a geometric line. And what you're saying, that separation, we call that an angle. Okay, we don't need to know by how much, by how many. We don't need to measure. We don't need to use the word degrees. We don't need any of that. In fact, if you go to another planet, maybe they have a different notion of degrees. Maybe they don't use the 360 for a circle. They don't use 90 for a perpendicular. Maybe they don't use any of that. Maybe they have other numbers for those same relations. Okay, so let's look at what an angle is for these people. Okay, And here's the unimaginable mathematical so-called physics angle. Okay, so that's what we're going to look at now. What is an angle? Well, it's a quantitative concept. It's how much. That's what they're interested in. They're not interested in the qualitative aspect of this. They're just interested in the quantitative. How much? How much wide is the mouth of the alligator? You know, that's what they want to look at. And it's got to do with measurement, numbers, units, degrees in this case. Could be radians, some other measure that you can come up with. Angle, two 1D lines. What was the line in mathematics? Motion. So you're saying that you need two itineraries, two trajectories, straight itineraries, right? To make an angle, according to mathematical physics, so-called physics. Okay? Straight, I don't know about straight because itineraries cannot be straight. You can say that ruler is straight, okay? Or the table is straight. You cannot say that you walk straight. The word is rectilinearly. I walk rectilinearly. Then you can use the word, this adverb to qualify a verb. But you can't say that walking is straight. Not in physics. In ordinary speech, you can say whatever you want. That's poetry. That's good. That's hyperbole. You can use whatever you want there. But in physics, in science, you have to use the correct language. That's what we're trying to teach here, the correct language. And you can't say you walk straight. You walk rectilinearly. That's the way you say it in science. Okay, let's get that straight. Okay, and there you have the mathematical line. It's a rectilinear itinerary. So to form an angle, they use two trajectories, two itineraries. Okay, and really you should represent those with dotted lines. They never do. What they have is these solid lines, which is wrong, because if they're going to talk about itineraries, what they're doing is putting one itinerary at an angle with respect to another itinerary. Okay, so they're talking about two itineraries. And is that an angle, or do we need two objects to create this pattern? Okay? Because remember, when you have motion, the only way you can reproduce that if you remember the previous locations. Otherwise, you don't know if you walk, right, straight, and another person walks straight in a different direction, right? You formed an angle between the two of you. But see, the problem is that you're just at the end points. You have location only at one place. You can't be at two places at once, like in quantum mechanics. Okay? So you're here in one place, the other guy's over there at another place, and the only way you can remember, that you have an angle is by tracing all the locations back to square one, to where you both, from where you both parted. Okay? So again, when you talk about itinerary, you only end up at one location, finally. And the only way you're going to get back is if you trace a line through all those locations and unite the two at a corner, the two itineraries at one corner. So that's the notion that they have in mathematics. Okay? And even worse, because they have one of these trajectories, it rotates, it opens up. So we have not only two trajectories, you're moving along these paths, as this fellow called it, and then the trajectories are widening out, and they're looking at that separation. So we have an itinerary that is moving and forming what? An angle, because that's what the line is. It's an itinerary. It's not a line. It's not a rectangle, an elongated rectangle. It's a bunch of locations. And once you build this location, this set of locations, now you're going to widen that. You're going to fan it out to form your angle. So you have a whole bunch of locations. You got to finish that line first, right? That itinerary, and now you're going to move the whole itinerary. You're moving motion to form the angle. That's the notion they have in mathematical physics. Okay, I hope that someone got that. So yeah, an angle is rotation of a trajectory, rotational trajectory of rectilinear trajectories. That's what it is. You're rotating the trajectory or the itinerary. Okay? And of course, they're interested in degrees or radians or whatever. And those are measurements. Those are units. And those have to do with numbers, with how many units of, you create a number or a unit. And then you say so many units is what this moved over. And so they're talking about motion, how much something rotated, not about the end result. The degrees is a measure of motion. Of motion of what? Of an itinerary. So I hope you got all that. What are some of the problems that this creates, these notions, these concepts that these people have of what an angle is? Well, here, let me give you a couple examples here. Here's the first one. Mathematical physics, perpendicular. What is perpendicular? Well, we say it's an angle. Okay? Again, perpendicular is a quantitative concept in mathematical physics and invokes two directions. Remember, but here you're talking about, again, motion. Okay? The direction in mathematical physics is not a static concept. It's motion in a given direction. And so we have directions that are moving now. Okay, so keep all that in mind. But direction is a qualitative concept. I mean, it doesn't even belong in math. Okay, so you have no use for direction in math. I can't put a direction in an equation. Okay, they do through velocity because velocity has magnitude and direction. Okay, but the direction part is the qualitative part, and they kind of put it in by hand. You know, acceleration, if you change direction, like in angular momentum or angular rotation, you accelerate even though the speed remains constant, you accelerate simply by changing direction. A qualitative concept that changes your acceleration, which is a quantitative concept. Okay? Keep all this in mind. So math direction is a dynamic concept. Okay? And this implies that mathematical physics, the perpendicular, the notion of perpendicular, is also a dynamic concept. So they're not talking about the final result for perpendicular, which is like that. They're saying that they're moving the stick that they put to represent direction, motion, right, itinerary. They're moving it, and that motion is the 90-degree angle. Okay, they have to put a number to that. And so you can see they always represent it with arrows. Okay, so here you see a comparison side by side. Okay, the physics perpendicular. Okay, it's perpendicular is qualitative. It's a static concept. Okay, we don't need to have anything moving. Perpendicular is something you see in a single frame of the universal movie. Perpendicular invokes the edges of two straight ideal figures. There you see the picture of the blue versus the red line. And a vertical figure versus a horizontal figure. That's what it is. That's a definition of perpendicular. The word perpendicular comes from the plumb bob that the masons used to use in the old days, and they would put the plumb bob to measure it against the horizon. Okay, so they would build a wall and they wanted to see if it was straight. So they would hang something, a weight from a string, and they would measure, check to see if the wall was straight. It was all qualitative. There was no 90-degree for that purpose. All they said is it's perpendicular. Well, what do you mean by that? Well, it's one is straight, one is vertical compared to the other one, which is horizontal. That's what they meant. And that's what it is. That's what it is for the purposes of physics, and that's what it is objectively in front of you. Okay, this other stuff that's on the left, the mathematical notion, 90 degrees, all that, that's for calculations that these people want to do to play around, you know, but then they come up with absolutely idiotic conclusions such that gravity is geometry. What do you mean geometry? Yes, the warping of this platform, which are a bunch of dimensions, which are a bunch of number lines actually, and we bend them. And it's the bending of space-time, right? Just this coordinate system that bends, and that's gravity. So you can see that it does have an effect on the minds of all these mathematicians who extrapolate the notions of geometry that they've created to reach conclusions, irrational conclusions, that, you know, rational people out there have problems swallowing. They say, what do you mean space-time? What is space-time? Well, we don't know. It's unimaginable because it's four-dimensional. Oh, it's like a four-dimensional object? Yeah, it is. Space and time. Time is a physical object. Well, you don't have to take it so literally. Those are the answers you get. And so, yeah, all these geometric figures, they come from these lines and points, which were misdefined from the start. And today, if you look those words up, they say, well, we can't really define these words. Yeah, they can't, because they're trying to define an object, and you don't define objects. You don't define the word table. You don't define the word rock, the word tree in science. You point and say tree, rock, table. Then you can describe it, but you didn't need to describe it to point and name it. You can't do that with a concept. Concept you must define. Rocks, trees, tables, you don't define. You just point and name. And so that's the difference. Okay? Objects you point to and name, and concepts you define. Okay, here's the wrap up on that. Here you have the mathematical physics dimension. What is a dimension? Well, according to mathematical physics, okay, this is the mathematics version, the minimum number of coordinates needed to specify any point within it. And see, they use these words like point and coordinates, and you say, oh, what was all that? Well, coordinate is a number. That's all it is. You look up the word coordinate and say it's just a number. So it ends up being a dimension is just a minimum number of numbers. Okay? And then they say any point, meaning a location, not a point. They use the word point, and that's very misleading because you don't know if they're talking about a dot or location. And they're talking about location. They're not talking about a point. Therefore, point is not part of geometry. Location is what they're referring to, and location is not a geometric figure, especially if it's alleged to be 0D, which it ain't, because you have what they have is like an ordered pair or ordered triplet. How to get to that location. The instructions on how to get there. That's what a point is. The instructions on how to get there, not what it is. It's not the location itself, it's how to get there. Instructions on how to find the treasure chest. Okay, so we have the number of numbers, and what is a number? It's to count. It's the verb to count. That's what a number is. Okay, and so I'll let you think about that for a long while, but that's what the word number is. It's not a noun for the purposes of science. It's a noun in ordinary speech, but not in science. In science, it's the verb to count. That's what number is, counting. Okay? And so dimension, coordinate, vectors, they're all dynamic concepts. And they all have magnitude and direction. They say vectors have, but they're all the same. All three are magnitude and direction because they're talking about number lines. And number lines have magnitude, but they don't have direction, actually. Only physical things can have direction. Okay? And number lines have no direction in great measure because numbers can go in any direction you want. You can go that way, that way, that way. I mean, look at a number line called time. Which direction does time flow or run or whatever they say? Whatever word they use to qualify that. No, time doesn't run or flow in any direction because time is not moving. It's not a thing that moves in any direction. You can say the cow moved in that direction. You can't say time moved in that direction. And time is a number line. It only has magnitude. It has no direction. Direction is a qualitative concept, belongs exclusively to physics, not at all to mathematics. Okay, so what are all these dimensions, coordinates, and vectors? They're rectilinear trajectories. In fact, you see there, that's a typical graph for Cartesian coordinates. And you can see they put arrows and they're all chopped into pieces. Because what they're really representing with those lines cut into segments, what they're representing is locations, numbers. Each one is identified with one number. And you can break those numbers up in gazillions of pieces, no problem, depending on your coordinate system or how you're going to use it. You can chop that up as many times as you want because they're not talking about direction. Direction you cannot chop into pieces. Direction is always like that. It's made of a single piece. And what they do, they chop direction to pieces because they're talking about what motion, and each one of those pieces is location. And each one is assigned a number so that you have this coordinate system. And that's why they put arrows, and that's why they chop the arrow, that long arrow, they chop it into pieces. Okay, so you got that. That's what they're putting in front of your eyes. And then they start giving you all this, this word wizardry in your ears that you're listening to, and you say, well, I can't make sense of what they're putting there and what this guy is explaining. Of course not. You're never going to make heads or tails or mathematics in that sense because mathematics has nothing to do with physics. What you're looking at is a physical thing that's hitting your eyes, that's objectively coming into your eyes, and they're asking you to interpret it in a given way, which is not what you have in front of you. What you have in front of you is motion. Each one of those segments is location. You build motion with locations, just like we do in our universal movie. It's got an arrow. That arrow is not a static direction. It's motion, direction of motion. And you have to walk, like in this case, example, you have to walk 2 paces to the right and 3 paces north, and you get to the point, which is a location, which is where you're at, where the treasure chest is at. Okay? And again, itineraries are rotated 90 degrees. So they rotated 90 degrees. Remember, those are itineraries, and they're to get their perpendiculars, their dimensions, because dimensions are orthogonal to each other. Okay? Length, width, and height are perpendicular to each other. And so they rotate them, because what they're talking about is not dimensions like length, width, and height. They're talking about number lines made of locations, each one with a number assigned to it, and they're rotating these to the 90-degree angle, to the perpendicular angle, meaning vertical versus horizontal. That's what it's all about.